Hi, this is Mr. Barron. I'm going to be showing you about the dissociation constant, and I'm also going to be talking to you about how to deal with pH equations. First off, we want to talk about an acid, particularly weak acids. If you have a weak acid, there is a way that you can write it out with an equilibrium expression. So say I have HA, and that's my acid, and it obviously dissociates because it's an acid and breaks apart into its hydrogen ion and into its acid. So this is writing it out as a Arrhenius definition, which we don't really need to remember the name for in the first place. But there's also Bronsted-Lowry definition where we have HA plus H2O. It breaks apart into H3O plus and A minus. I'm going to be using this definition for the problems that we're going to be working with, but either of them work fine. So let's take a look at this equation one more time. So I've got HA dissociating into H plus and A minus. I can write it out as an equilibrium or K in terms of concentration, and of course it's the products over the reactants, so it would be H plus A minus over HA, which is just the same thing that you did when you were dealing with previous problems involving equilibrium. All right, this Kc we actually rename as K sub A, and we call this the acid dissociation constant. So we're going to be dealing with a sample problem involving the acid dissociation constant. I want you to pause this recording, and I want you to turn to page 687. On page 687, what we're going to be doing is we're going to be doing the practice exercise that's on the top right. And what it tells you is that you have this solution of niacin, and the given information you have about the niacin is that it tells you begin with a 0.020 molar solution of niacin, and it has a pH, we already know the pH, of 3.26. Okay, they draw out the molecular structure of it. All right, now because they give you a structural formula, they don't give you a chemical formula. The structural formula shows that there's a hydrogen, and the hydrogen's obviously going to dissociate. So we could write it out as niacin, and then it's breaking apart into H plus, and then obviously whatever's left of niacin, but obviously it has a negative charge now. An easier way to write it out perhaps would be just to write HA in equilibrium with the hydrogen ions and what was attached to the hydrogen before it dissociated. To solve this problem, I'm going to need an ice table because the question's asking for what the percent ionization is. Now, let me review what percent ionization is. Percent ionization is going to be the same as your hydrogen ions concentration over whatever your original acid is. And in this problem, it's going to, of course, be niacin. Now, what you're going to do is you're going to take the pH and you're going to use that to figure out how many hydrogen ions are in solution at equilibrium. So since we're dealing with equilibrium, you need to get out the ice table. Now, what's at equilibrium? For the hydrogen ions, I'm going to write pH is equal to 3.26, which we also know is equal to the negative log of hydrogen ions. So what I'm going to do is, in my calculator, I'm going to have to solve for that H plus in here. To do that, I'm going to take 3.26, and make sure my light's on so that you can see this, negative 3.26, because I'm going to have to take this negative to the other side. So let me rewrite this one more time. Negative 3.26 is equal to the log of hydrogen ions. It's because I multiplied both sides by -1. All right, so now I'm going to have to take the anti-log of this, which is basically making it, since these are all base 10, 10 to the x. So in my calculator, where it says log, I'm going to use that function, which is to the top of the button. So I'm going to hit second, and it's 10 to the x, and my x is going to be this value right here, negative 3.26. Cap off the parentheses, hit enter, and that is my concentration for hydrogen ions. So my hydrogen ion concentration for this problem, H plus, is equal to 5.5 times 10 to the negative fourth, and that's of course in molarity. So this can go in for the equilibrium value, 5.5 times 10 to the negative fourth. Now this is really critical here. We know that's at equilibrium because they tell you what the pH is. This information right here, that's your initial. It tells you that's what you started with, and then you ended up with a pH. If you use the pH to figure out the hydrogen ion concentration, this value down here, that means it's at equilibrium because it's obviously dissociated and lowered the pH. So I'm going to plug in this initial concentration for my original acid right here, 0.02. And then I know initially I began with no hydrogen ions. So now I just have to fill in all the blank spaces in my table. And conveniently everything is a 1-to-1-to-1 ratio, so I don't have to deal with coefficients for any reason at all. So this, obviously my change was I had to add 5.5 times 10 to the negative fourth. Well, since it's a 1-to-1-to-1, it means that the change is the same for each of the other substances in this table. The only difference is that this one is losing that amount, 5.5 times 10 to the negative fourth, because this is dissociated and producing these two. So the answer down here is going to be 0.02 minus 5.5 times 10 to the negative fourth. And this one is going to be 5.5 times 10 to the negative fourth. Alright, so now what I'm going to do is I have to figure out the percent ionization. To figure that out, I have all the information I need. This is the hydrogen ions that came from this. So my percent ionization in this particular problem is going to be, my percentage is going to be 5.5 times 10 to the negative fourth over 0.02. And then of course you convert that into percentage and you end up with something really close to 2.7%. That is your answer for part A. Now part B wants you to figure out the acid dissociation constant, and that's K sub A. K sub A will tell you how strong the acid is, because the bigger K sub A is, the more of your products exist, because remember K sub A is always going to be your products over your reactants. So if you have more products, meaning it's more acidic, more of it is dissociated, it's a stronger acid. So Ka can give you a relative value of how strong your acid is. So I'm going to write equals, and then I'm going to plug in my numbers. So it's 5.5 times 10 to the negative fourth times 5.5 times 10 to the negative fourth, all over HA, which is 0.02 minus that other value, which is 0.02 minus 5.5 times 10 to the negative fourth, and you get a number that's close to 0.0195. Once you plug that all in, you'll get the same correct answer that you see in the textbook for B, which is 1.5 times 10 to the negative fifth. If you have any other questions, let me know.